Hello and welcome to Chapter 16 of Earth Science, the atmosphere, composition, structure, and temperature. So in this chapter, we're going to look at sort of the layers of what we breathe in every day, the air as you go up into, well, near outer space. We're going to look at the differences in temperatures and pressures and how the sun plays a role in the seasons and how everything is interrelated between the earth and the sun. You deal with this every day. I mean, if you watch the weather, the weather is created by the sun and it affects everybody on Earth, obviously. And so all of this interplay determines, along with the Earth's position in space, whether we're tilted away or towards, gives us the seasons like winter, right now it's winter, or summer. And we're going to talk about all of those different things and looking at what truly makes up the air we breathe, so to speak. Let's get right into it. So weather and climate, what's the difference? So weather is sort of what happens today. Is it going to rain today or maybe rain tomorrow? Is it going to be sunny, partly cloudy, or partly sunny? What's the difference? Anyway, and it's always changing. So one day it might rain, the next day it might be clear. And in Wisconsin, Milwaukee, one day it might snow, then we might get rain, and then it might be 50, 60 degrees. We never know. The difference with the opposite of that is climate, which is sort of over a long period of time, sort of normalized, generalized over a long period of time. So here in Wisconsin, we're in sort of a temperate climate zone where we have four seasons. We have winter, we have spring, summer, and fall, and we have sort of normal ranges of temperatures. Can it get hot here? Yes, but is it like desert heat, like in Arizona or let's say the Sahara Desert? Not typically. We're very rarely do. I don't even think we've ever gotten above 110 here. I don't know. Maybe we have. And just like severe cold, it can get very cold here, but is it going to get Antarctica cold? Probably not. And then also you have to look at the elements of both weather and climate. And those are the things that are measured, right? Things like temperature we measure every day. We want to know what to wear, so we want to know how hot or cold it is. What's the humidity? In the winter things are very dry. You feel itchy skin, things like that. And in the summer you sweat almost as soon as you go outside because there's a lot of humidity. How much cloudiness is there? Is it partly cloudy, mostly cloudy, partly sunny, mostly sunny? Again, those are meteorological terms. I don't fully understand the breakdown of them. And then precipitation, obviously, is it rain, snow, sleet, somewhere, hail, tornadoes? What's going on? And then air pressure, which is more of a scientific thing. Most people in their daily lives don't really worry about air pressure, but from a climate or like, if you're a meteorologist, what air pressure kind of tells you, helps you forecast what's to come. If the pressure is slowly lowering, we know there's a low pressure system there which is typically for us means that we're going to have unsettled weather, usually some type of rain or snow event. Not always, but a lot of times. Then you have wind speed and direction. Wind is caused by the sun, and it can get pretty windy here. We get some pretty windy days. It's nothing like the Great Plains. It's always windy out there. But you want to know which direction that wind is coming from. In the winter, if the wind is off the lake, it's typically warmer, which is kind of weird because in the summer, when the wind is off the lake, it gets cold. I've been down on the Summerfest grounds in June and freezing because that wind just came off the lake and it just wasn't, the lake water's too cold still. So all of these things play a role in both weather and climate. The difference being weather is daily, climate is sort of over a long period of time. So let's look at what actually makes up the air that we breathe, the gases that we inhale and exhale, so to speak. Well, inhale at least every time we breathe. Now, you may or may not have known this already, but the bulk majority of the air we breathe is nitrogen, not oxygen. While the human body requires oxygen to survive, the vast majority of what we're breathing in every time we breathe is 78% nitrogen, 21% oxygen, and that leaves 1% for a bunch of other stuff. Um, so, there are some other things like argon, which are noble gases, and things like that. Obviously, carbon dioxide, which if you breathe too much of, you can die. Um, so we don't want to do that. But the bulk majority of the air composition of the air in the atmosphere is made up of nitrogen. So here's a graph of that. So you can kind of see some of what's going on here. Obviously, the vast majority of it is nitrogen. You have the part that we care about, the oxygen that we need to breathe. Carbon dioxide, which is again a greenhouse gas, which we'll get to in a bit, not something we want to breathe in. It's actually poisonous to us. That's what we exhale out. So when you breathe in, you're breathing in the oxygen in your body. When you exhale out, your body is converting that into carbon dioxide. And so you don't want to keep breathing that in. That's why you want air circulation, and that's why we need trees, because the trees take that carbon dioxide, suck it up, and convert it back into oxygen. So that's a whole nother lecture. But you can see there's some other things. Argon is by far the of the lesser known quantities. Argon is the most. It's what we call a noble gas. It doesn't react with anything. Same thing with neon and helium and krypton. There's very small amounts of those in there as well. So one of the variable components of air is water vapor. Now water vapor is up to 4% of the air's total volume. And that's where we get clouds and we get precipitation and fog, things like that. So you can see that image that there's sort of these low-lying clouds, and that's all water vapor. A lot of people might call it steam, which technically is water vapor, but that's from heating. This isn't necessarily from heating, it's from water vapor being sort of condensed in the air. And it absorbs energy, heat energy from Earth. What that means is it's kind of sucking up that heat and creating sort of a warmer layer of air near the surface that condenses all of that water. Another variable component of air is what we call aerosols. Now, when you think of aerosol, you think of like spraying a can, and that's sort of this idea is that you have these tiny little solid or liquid particles. You could almost think of it like dust or sand or whatever it is that gets caught in the air, and then water vapor can condense on these and create things like dust storms and all kinds of weird phenomenon. As you can see in the image, I'm looking at my other monitor here. That's off the coast of China. So they have these huge dust storms, and unfortunately, Japan kind of gets nailed with all this stuff, and so does Korea to a certain extent. What these aerosol particles do is they reflect sunlight. So they take the sunlight and bounce it sort of right back up into space. And that's what those particles in the atmosphere is why we get those vivid sunrises and sunsets. In some areas, you don't get them as much. The air might be super clean. But in a lot of places, you get these bright red or dark red sunsets or sunrise. That usually means that the sunlight is going through a thicker layer of these aerosols that are stuck in the atmosphere. While it's pretty, it's not necessarily what you want to breathe. A great example of this is whenever there's a volcanic eruption, you'll see a lot of areas that are sort of downwind from where the um, volcano is, or depending on how big the eruption is, it can go worldwide. You'll have these sort of more prettier than normal sunsets. The other one with that is, and we just had this last summer, were the massive wildfires out west, especially in California. Wildfires create ash. That ash gets up in the atmosphere and breaks down into tiny little pieces. And once again, that's where you get these really crazy, vivid sunsets and sunrises. Another variable component is what we call ozone. Now, normal oxygen is found in pairs, O2, like CO2. That's what we breathe, breathable oxygen. But there's also this thing called ozone, which chemically is three oxygens combined. It's poisonous if you breathe it by itself, but it's a necessary component of Earth's atmosphere. But it's not distributed uniformly all the way around the Earth. It's sort of concentrated in some areas, you typically between 10 and 50 kilometers above the surface. So it's pretty far up there. Now, what this does, what ozone is good for, is that it absorbs the harmful UV radiation from the sun. Without that ozone layer, we'd all be a lot tanner and there'd be a lot more cancer, skin cancer. The ozone layer is what protects us from a lot of the harmful rays of the sun. Now, does it protect us from all of them? No, it does not. But it does protect us from a vast majority of the really harmful UV rays coming from the sun. Now, you've probably heard of the ozone layer up in, over the Antarctic polar regions, and there was a group of chemicals called chlorofluorocarbons, which were used in a lot of spray cans and things like that. And they found out that these chlorofluorocarbons were reacting with the ozone in the atmosphere and combining it to create something else, depleting that ozone and creating essentially a massive hole directly over Antarctica, where a lot of the sun's rays were allowed to come in almost uninhibited. So this was a huge issue, and there was a global, essentially banning of all CFCs. And as of now, this year, 2020, as of 2020, the actual hole in the ozone layer has essentially at least about 80% healed itself. It's mostly gone just by eliminating those chlorofluorocarbons. So that's a bit of good news when there isn't much going on right now. But so that was one thing that just by banning that particular class of chemicals, we were able to massively reduce and help repair this damage that we had done to the atmosphere. So here's what it looks like. So in 1979, you can see there was a little bit of a hole here. I mean, it wasn't huge, but in 2012, you could see almost all of Antarctica was left, uh, to fend for itself. And it's not in this particular image now, but I just saw one online that as of 2020, it looks more like 1979 now than it does 2012. So in the span of 8 years, we've managed to help repair itself, not quite all the way back, but very close. All right, so let's look at the structure of the atmosphere. So this is sort of that layer cake going from the ground and then going upwards towards space. Now, the air pressure changes, and pressure is the weight of the air that's sitting on you. So as you sit on, let's say I'm sitting on this chair, there's some weight being exerted on me by the column of air that sits above me. Now, that column of air can weigh more or less depending on sort of the situations taking place in the atmosphere. So, the average sea level pressure is what they call about 1,000 millibars or 1 bar. That's not important, you know, but it exerts about 14.7 pounds per square inch. Now, the human body is used to this weight because that's where we live. We just evolved to understand, our bodies just get it. We we live our lives with that type of pressure all the time. Now, if you go down deep in the ocean, as you go deeper and deeper into the ocean, you have more water on top of you to the point where if humans were to go deep enough without any sort of like submarine or anything like that, they would just get squished. The weight of the water would just squish you. So when they travel to the deepest parts of the ocean, they need a specially designed, very strong, very strong vehicle to get you down there, because by the time you get to the deepest parts of the ocean, which are about 29,000 feet deep, it's something like 30 elephants sitting on you. So if something cracks down there and breaks, you're instantly smushed into nothing. It's just instant because of the weight, all of the weight of the water. Now, the opposite is true with the atmosphere. So as you go up in the atmosphere, the pressure decreases. So you have less air on you. So as you go up in elevation, so you get less and less air pressure. Now, again, the human body isn't going to notice that at first until you get way up there. But the way you do understand that is as you go up, you have less oxygen to breathe. So it's the same sort of thing. We would call it air pressure, but for us personally as humans, we would have a harder and harder time breathing because there's less and less air pressure, meaning less and less to breathe. So 90% of all of the atmosphere is below 16 kilometers of height or 10 miles up. So when you go 10 miles up, after that, there's very little atmosphere left. There's some, it is there, but not much. All right, let's take a look at this, how this works. So you can see in this graph that the air pressure at sea level is about 1,000. And that's down here, wait, right here. But as you go up in altitude, you also lose you also lose air pressure. That's why it's sort of this negative effect going in this direction. So when you get to the top of Mount Everest, we went from 1,000 millibars at sea level to 314 millibars, excuse me. So we lost almost 700 millibars just at the top of Mount Everest. And what that means is if you're going to climb Mount Everest or any of those super tall mountains, you have to have a respirator. There's not enough oxygen at those altitudes to breathe. There's not enough air pressure to get the air into your lungs, so you have to have help. Now, if you go way up there, you had this U.S. Air Force Captain Kittinger, who went up 31.3 miles in a balloon, and up there the air pressure is only 9.6 millibars. Think about that. So we're at 1,000 here at sea level, and in Milwaukee, if you're wondering, Milwaukee is only 627 feet above sea level. So we're not that high up at all here in Milwaukee. Um, in fact, we're really low compared to a lot of other areas. And if you look at Denver, they call Denver the mile high city. That's because their elevation is 5,000 some odd feet tall. There are just standing on the ground. That's not a mountain. That's just where you are. It's just the ground slopes upwards as you go west towards the Rocky Mountains. This mountain here is 29,000 feet tall. Okay, and uh, and actually I misspoke in the previous slide. So Mount Everest is 29,000 feet. The deepest part of the ocean is actually 35,000 feet deep, 34 or 35,000 feet, somewhere in there. So there's about 4 to 5,000 more feet of water than Mount Everest is tall. But um, you get the idea. So the higher up you go, the less and less air there is to put pressure down on you. And obviously it becomes harder and harder to breathe. So they have names for all these sort of layers of the layer of the atmosphere. The lowest one that we live in is what's called the troposphere. So that's the bottom layer. That's the closest one to the ground, and the temperature decreases with altitude. So as you go up, it gets cooler. And if you've ever been up high enough, you may or may not have felt that. Um, so it's about 3.5 degrees for every 1,000 feet. And you could feel that depending on where you are in the world. Now, I spent the summer in Los Alamos, New Mexico, which is at 7,200 feet above sea level. And yeah, it got hard to breathe at times. I tried going jogging once and almost died. Um, so you can get pretty far up there, and you do feel that. Now, I was out there in the summer, um, so it's a different phenomenon. It's a dry heat, but the sun's rays are super intense, but it's not super hot. I hope that makes sense. So I got out of the car to look at something. I was literally out of the car. I can't even make this up. Less than a minute. I just got out of the car to kind of look over the edge and got back in my car, and I was burnt. So the sun's rays, you're closer to the sun at 7,200 feet above sea level, but it wasn't. That's the intensity sort of the sun, but it wasn't super hot. It was like 85 degrees. Whereas if I was at sea level, or like Death Valley in California, that same weather in Death Valley where it's below sea level, they can get up to like 120 degrees out in the sun. So, but because I was up at 7,200 feet, it's already cooled off a little bit. It doesn't allow it to get as hot. Now, the outer boundary or the top of the troposphere is what they call the tropopause. And you'll see that with these other ones. So then you have the stratosphere, which is typically where a lot of airliners fly and things like that. They fly up in the stratosphere, or the lower stratosphere. And then the outer boundary of that is called the stratopause. And then you get up into the mesosphere, um, which is 50 kilometers to 80 kilometers, and that's getting pretty high up there. There's not a whole lot up there besides, when you're traveling out to space. Temperature decreases. You can see in this, I failed to mention, in the stratosphere, the temperature actually increases at the top, and then it comes back down again. You'll see that in a graph I'll show you in a couple slides. And then finally, we have what's called the thermosphere, which is there's no well-defined upper limit because then you start getting out into space. And it's a fraction of the Earth's atmospheric mass, so there's not a whole lot up there, and you get gases moving at very, very high speeds. Let me show you an image of all of this. So here we have the atmospheric layers, and again, we're down here in the troposphere, and that's where most of us hang out, right? So the idea is you can see Mount Everest there. That's 29,000 feet tall, right? Most jet airliners fly at around 30 to 35, so they're actually in the stratosphere, the lower area of the stratosphere. Then you got the ozone layer in here. You could see, and here this red line here, you could see that the arrow temperature decreases, and then throughout the stratosphere it begins to increase again, and then it decreases through the mesosphere, and then it increases as you go out into space. The reason why it increases as you go out into space a little bit is because there's less and less um, atmosphere to the rays of the sun are more intense up there because there's nothing to block them. Now we need to look at how the Earth and the sun are related in terms of, we know that the Earth rotates on its axis, and then the Earth is also spinning or revolving around the sun. And because of this phenomenon, we also know that Earth is not straight up and down, it's tilted by 23.5 degrees, which I'll explain in a bit. And because of all these things, because we revolve around the sun, because the Earth is rotating, and because of that angle, we get things like day and night and the length of daylight, which is the change of the seasons. Let me show you some graphs of these, some photos. So here's the changing angle of the sun. Now, on the longest day of the year, which is the first day of summer, you have the sun at approximately 73.5 degrees at 40 degrees latitude. Now, if you don't know this, Milwaukee sits at 43 degrees latitude. So we're only slightly more north than what this image is trying to get at. The point of this image is to show you why we have long days in the summer and short days in the winter. And I'll show you all of those. So in the summer, we have roughly a 73.5 degree angle, which isn't quite vertical because to get vertical, you'd have to be at the equator, but it's way high up in the sky. So you get a much longer day where the sun is setting at almost 9 o'clock local time. Now, twice a year, we have what's called the both the vernal and the autumnal equinox, where the sun is exactly halfway between its longest and shortest day. So this would be these equinox would be the first day of spring and the first day of fall. And both of those would be at roughly 50 degrees of sun angle. So that's where we have essentially 12 hours of day and 12 hours of night, right? Half and half. And that happens twice a year. So and then we finally get the last one, which is the first day of winter, which is around December 21st or 22nd, which we just had not even a month ago. So there we have the shortest day. The sun is lower in the sky. We only have about 26.5 degrees of sun, and therefore we have a much shorter day with the sunsets around 4:30 in the afternoon. Nobody likes that. I don't even mind the cold. I just hate all the nighttime, all the dark hours. So this is because of the tilting of the Earth that we get these long and short days and our seasons. And I'll show you some more examples of this as we go. To get a better understanding of the differences in the seasons, let's take a look at the angles again. In the last image, you kind of understood it, but if you're in the tropics at the equator, that sun is straight up and down on you, and that's what this 90 degrees is. And that's why it's so hot in those particular areas. You have rainforests and things like that. The sun is, the term is beating down on you. It literally is in the equatorial regions because the sun is coming straight down because it's always there at the equator. Now, in some of our areas, like here in Wisconsin, we have a temperate region. So we're sort of in between the tropics and the polar regions. And we get, let's say, 45 degrees of sun. which gives us, again, the seasons. This would be sort of spring and fall. It's not summer, it's not winter, but it's kind of in between. And then in the polar regions, you get um, even less angle here. You have 30 degrees, which makes the angle of the energy come in at even a shallow, it's even shallower, which means they get less energy, less sun, shorter days, and colder temperatures. Now, the seasons, like I mentioned, are caused because the Earth is tilted at, oh, I think I misspoke before. It's 23 and a half. I think I might have said 25 and a half. I apologize. 23 and a half degrees. So it doesn't sit straight up and down. It's tilted by 23 and a half degrees. And that 23 and a half degrees is where we get those the changing of the seasons. So if you look at this image here, you can see the sun rays are coming in here, right? Now, the sun rays are longer where we are, way over here. In this particular image, where we are, which is right here, this is Wisconsin area, okay, the Earth is tilted away from the sun. So for us, in this image, this would be our winter. But if you'll notice in the southern hemisphere, down here in the south of they're tilted towards the sun in the southern hemisphere. So, and this is weird to a lot of people. When we have our first day of winter, Australia is having their first day of summer. So when we celebrate Christmas, winter's just starting for us, and in Australia, their summer is just starting at Christmas. It's very, very foreign to us up here in the northern hemisphere to think of something like that. But it all has to do with that 23 and a half degrees of tilting. So when the earth is spinning around the sun and it's tilted away from the sun, we're in winter, and eventually it starts to change that tilt towards the sun, and then we get towards our first day of summer. So here are those particular days. So we have the summer solstice. This is the northern hemisphere where we live. The summer solstice or first day of summer, the rays are over the Tropic of Cancer, which is the latitude that's 23 and a half degrees north. Okay. To visualize that, I think I have an image for you, but that's just south of Florida. 23 and a half degrees, I believe. I could be wrong about that whole. And then in the winter solstice, the vertical sun's vertical rays are at the Tropic of Capricorn, which is 23 degrees and 23 and a half degrees south. And that's where our first winter is because the Earth is tilted away from the sun for us in the northern hemisphere. And then you have the different equinoxes. You have the autumnal equinox. You have I got I accidentally duplicated these. Sorry about that. And the spring equinox, which is where the sun is at the equator, 0 degrees latitude. So for us in the northern hemisphere, that typically means we get roughly 12 hours of daylight and 12 hours of nighttime. So here's an image showing you the various angles and the lines that show you where the sun rays are concentrated. So if we look at the top image here, we'll start with the spring equinox. So this is where we have 12 hours a day, 12 hours a night here in the northern hemisphere. You can see the sun's rays are directly on the equator right here. You have the Tropic of Capricorn, which is 23 and a half degrees south. You have the Tropic of Cancer, which is 23 and a half degrees north, and the Earth is spinning. So now we come around here to the first day of, excuse me, first day of summer. Now the sun's rays are directly on this Tropic of Cancer, which I said is just south of Florida, the tip of Florida. So the sun's rays are right there. That's where we have our warmest parts of the year. So we get more direct sunlight because we're tilted towards the sun. Then as we move around, we essentially end up in the same position that we were at the spring equinox, but now we're tilted the other direction, even though it's still at the equator. And now we're going to have our first day of fall, which is typically near the end of September. And then finally, we move over here to the winter solstice. And now we are tilted away from the sun. The sun's rays are directed at this lower southern line, which is the Tropic of Capricorn. We're up here in the northern hemisphere, And so we get less daylight and less sun energy, hence winter. And then obviously you come back around again to spring. And it just keeps repeating that process. So here's another image kind of showing you the first day of winter, first day of summer with the various tilting. So in the first day of summer, you can see here that the amount of sunlight you get. So this is why it's always daylight up in the polar regions. They get 24 hours of sun. We get roughly 15 hours of sun here. All right. And that's in the summer. Now, when the Earth is tilted away from us, the polar regions get no sun, and we get roughly about 9 hours of sun or so, maybe 10 hours of sun. But the southern hemisphere gets all that warmth in what would be our winter. It's their summer. And then for the spring and autumnal equinox, it's pretty much half and half. Everybody gets pretty much 12 hours everywhere on Earth. We can't talk about the atmosphere without talking about atmospheric heating because the sun is always there during the day at least and at night, and it affects everything we do in terms of our weather patterns and our wind patterns. So we have to talk about how heating works and cooling works. And heat is always transferred from warmer to cooler objects. It's much easier for the term that they use in physics is equilibrium. And it's everything wants to be at sort of we'll call it room temperature for lack of a better word. So if I have something hot and I have something cold, eventually they'll make their way to sort of that cooler, excuse me, cooler uh, happy medium. Now, this is done several ways. One is through conduction. So it goes from the hotter part to the colder part, and I'll show you examples of that. The other one is convection, where you have sort of like, rotating heat generated going up and then back around and up and back around. And then you have radiation, usually electromagnetic radiation from the sun itself, which is traveling at the speed of light or 186,000 miles per second. Very quick. That's why it takes about 8 minutes for the sunlight to get to reach Earth. So here's the various different aspects of heat transfer. So we have conduction. So you heat up this pan. The heat itself is giving off radiation. That's what these red squiggly lines represent. That's heating up the water, but it heats it from the bottom to the top, creating sort of this rotational type of thing. You can see that with these arrows here. So cold water sinks, gets heated, hot water rises, and creates sort of these rotational type things. But at the same time, the pan is also getting hot, which then heats up, conducts that heat from the pan to the handle. That's conduction. So once something gets heated up, that heat starts to spread out depending on how hot it gets. It'll determine how much it spreads out. Now, if I take that pan off the heat, you lose the radiation. So therefore, you're going to lose the convection cells, so to speak, in there. Those will start to cool down. And then instantly, it'll go from hot to cold because that's just everything wants to go from warmer to cooler. It helps that it's what's called equilibrium. It wants to get back to equilibrium, what we refer to as room temperature. That's not really a scientific term, but I figured that's what you would understand. So everything wants to get back to sort of room temperature. So radiation means a lot of things when it comes to heat transfer. There's gamma rays, you can't see those. X-rays, which you get like at the doctor, which are harmful to humans. Ultraviolet rays, which is what makes you like if you go to a tanning bed or something, makes it. But again, too much of that is very harmful. Can give you skin cancer. You have the visible light that we can actually see. We have infrared, which now can be used like they have. Infrared heating for like stoves and things like that. And then you have microwaves and radio waves. All of these things are electromagnetic radiation. Some things, any one of these, if you have too much of it, can heat things up. So here's an image of the entire electromagnetic spectrum. Now, if you didn't know this already, What we actually see with the human eye is a very, very small portion that fits right in here. That's what we call the visible light spectrum. Now, if you've ever seen a rainbow, you can see the various colors, and there's an acronym called Roy G Biv. Roy is, ROYGBIV. So it's red, orange, yellow, green, blue, indigo, violet, and that represents all of the colors going in this direction. Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. Now those are the ones that we can see with the human eye, but there's a lot more than that in terms of you have microwaves and infrared waves and ultraviolet and X-rays and gamma rays and all kinds of stuff that has to you need some sort of special instrument to be able to detect. There's also gravitational waves, which are that's a whole nother ball of wax. Electromagnetic radiation follows some basic laws. All objects, at whatever temperature they're at, emit some kind of radiation. I know it sounds weird, but it's true. Hotter objects radiate more total energy than cooler objects do, right? Because we can feel that. If I turn my stove on for a little while and then turn it off, it's still radiating energy because it's hot. Whereas a cold stove, you don't feel it because it feels like it's the same temperature as maybe your hand or something. The hotter the radiating body, the shorter the wavelength of the maximum radiation. So, like infrared can really heat up, a lot of that gets into things like lasers and stuff like that, where they emit a very, very specific frequency, and you can cut steel with those things. Objects that are good absorbers of radiation are good emitters as well. And that uh, pots and pans are a perfect example of that, like the image that we saw on the previous slide. We use metal pots and pans because metal is good at conducting, absorbing that energy. Okay, and it also emits it as well. So in terms of emitting it inwards, so they're uniform in heating up things like let's say water or whatever you're cooking. When radiation comes off from the sun and is coming towards Earth, the atmosphere is pretty much transparent to it, meaning it can go right through a lot of it. Now, when it does that, it has some options. It can either be reflected or what we call albedo, which I'll mention in a bit. It can scatter, you know, um, because of things in the atmosphere that help it scatter, like the ozone layer helps absorb, or absorption, which is like the ozone layer, which helps absorb UV light. Now, most visible radiation reaches the surface. Obviously, that's why we see a blue sky because it's emitting these these wavelengths of light, and what's reflected back sort of into the sky is the blues in the visible light range. And about 50% of all of the solar radiation is absorbed by the surface of the Earth itself because, rocks and everything absorbs that energy very, very efficiently. So you can see in this image here, we have 100% radiation coming in. When it comes down, 50% of it is directed or diffused by land and water. Now, granted, 71% of the Earth is ocean, so that includes the ocean. You have 20% reflected from clouds. You have 20% absorbed by clouds. You get it's about 30% that's reflected back into space. So there's a lot going on here in terms of where the energy from the sun ends up, and it's a good thing that we don't get all of it, because the problem with that is we would fry down here on Earth. So we need the clouds to reflect it back. We need the clouds to absorb some of it. We definitely need the land and oceans to absorb a lot of that solar radiation. Otherwise, the whole Earth would be a lot hotter and a lot more dangerous to live on. Now, I mentioned albedo before, and albedo is just how the sun's rays reflect back out, let's say, into space. Now, a lot of that has to do with the surface, both through a lot of it is just through color. Okay, so something like a dark roof like that, or a light, is dark roof, the darker the color, the more it absorbs. So that's a lower number. Look at the asphalt, it's 5 to 10% albedo. That means 90 to 95% of the rays coming that hits asphalt, 90 to 95% of it is getting absorbed. This is what's being reflected. The numbers you see in this particular slide is the amount being reflected back. So the darker the surface, the less is being reflected back. Now you can see that like it's snow is 50 to 90%. So especially in like the polar regions, the reason part of the reason they stay cold is because a lot of the energy coming in is being reflected off the ice and going right back into space. Obviously, a lot of that has to do with the angle of the Earth and everything else. But a part of that is that a lot of the energy, because of the white, all the white from the snow and everything, is being reflected back into space. One of the problems with certain types of radiation is that it kind of gets stuck in the atmosphere and it's absorbed and then re-radiated, and one of those is, like I mentioned earlier in the lecture, is carbon dioxide. So carbon dioxide unfortunately acts as almost like a barrier. So when the energy is coming in and it comes back up, it reacts with the carbon dioxide that doesn't allow it to go back through. It sort of traps that energy between the surface of the earth and where the carbon dioxide layer is. That's why we get things like smog, and especially in like highly urban areas with cars and things like that, you get things smog and bad air quality. That carbon dioxide sinks. It's heavier than oxygen and just kind of hangs there in the air. This is what we call the greenhouse effect, and that's why things like cars and deforestation, cutting down the rainforest is such a big thing. Trees that have green leaves do what's called photosynthesis. Now, maybe you've heard of that, maybe you haven't, but what they do is they take the carbon dioxide, plants take the carbon dioxide in the air, and they sort of suck it into their leaves where they can use it for good, and then they emit oxygen, which is what we need. That's why trees are so important to the health of Earth, not just me or you or any, but the entire atmosphere. And so you have these large areas of the rainforest being cut down for things like grazing for cattle and stuff like that, and it's negatively affecting this is where they believe a lot some of the climate changes along with cars and everything else. The fewer trees you have, the less carbon dioxide can be sucked up. So this is where it all plays a role with one another. You have the cars emitting the carbon dioxide, the lack of trees to help suck it up. Those two things combined give us what's called global climate change. So this image here kind of gives you an appreciation for the different extreme ranges, so to speak, of what greenhouse gases can do. So on the moon, for example, there's no atmosphere. So any incoming energy is automatically either absorbed or bounced back into space. So all outgoing long wave energy is just put back out into space. So that's easy, right? But here on Earth, it's a little bit more complicated. So um, you have incoming solar radiation, right? And then you have some outgoing radiation absorbed by the greenhouse gases. Now, the greenhouse gases then turn around and re-radiate some of that energy back towards Earth. And this is where the problem lies. It creates sort of this trapped amount of atmosphere that can literally raise the temperature, all right, by enough to cause global climate change. Now let's look at the other extreme on the right here, which is Venus. So on Venus, their atmosphere is almost all carbon dioxide, and so the energy from the sun is almost all being um, trapped at the atmosphere and can raise the surface temperature by as much as 941 degrees Fahrenheit. So it's really hot on Venus, and a lot of that has to do with the fact that, well, obviously Venus is closer to the sun, but because of all of the carbon dioxide in the atmosphere, it's just re-radiating that energy over and over and over and building and building and building that eternal heat up because it's trapped there just above the surface. Now, temperature measurement is one of those things that we all sort of are interested in. That's why we have weather on the news, right? We have the daily maximum and minimum temperatures. How hot is it going to get? How cold is it going to get at night? Daily mean temperature, things like that, where they average them over time. Daily range, which is the highs and lows. Obviously, the monthly average, the annual average, things like that. We're, as humans, kind of interested in this stuff because, again, we want to know, what do we have to drive in? What should I wear? What was and even like, what was the temperature last year? You see that a lot on the news. Oh, last year we had 60 degrees, and this year it's 20 below zero. I mean, those are kinds of things that when you live in a place, you're interested in because you want to know what's going on. So the way they do this is with maps that show sort of continuous lines of temperature, what we call isotherms. They're lines of equal temperatures on a map. And you could see the thermal gradient is the amount of temperature change over distance. So if it's really wide, you might have long, big areas of warm weather or cold weather. And if the isotherms are close together, you can go from vast temperature changes in a short amount of distance. So here's an example for, you've seen this on the weather all the time. They make these pretty maps. So for example, we're right here. All right. So we would rate on this map, we'd be in the 50s. You see it here in Milwaukee at 52. And so what they're doing is what we use the term is interpolating. So they're creating these lines, and everything within those lines is a um, similar type of temperature. And again, you've seen this every night on the news. And then what they'll do is create several snapshots and sort of play them forward like a forecast. What's going to happen in the future? Now, the land heats up more rapidly and to a high temperature than water. Water absorbs the energy, but it takes a lot more to heat up water than it does to heat up the land, right? Think of a hot summer day. So if you're walking on the beach, right, the sand can get really hot on your feet. So what do? You go step in the water to cool off your feet. The water's not going to be the same temperature as the sand because it takes a lot longer for water to heat up than it does um, the sand. So water has a high what we call specific heat, or the amount of energy needed to raise it 1 degree of Celsius. And that's a good thing. It's a good thing and it's a bad thing. It's a good thing because it helps moderate temperatures, but sometimes, we would always like the water to be a little warmer because up here in the northern portion of the U.S., that water gets pretty cold. So you can see in this graph here the differential between land and water. So this is off the coast of California. And you can see that this is all ocean out here, these greens and blues. So down here, the temperature here is anywhere between 34 and 50 degrees Fahrenheit. And then you go out here and you got some seriously high temperatures. I know I should probably use a different color marker here. So down here, out here, that's Death Valley type stuff. Actually, I think Death Valley's over here. But you get the idea. Very, very, very hot temperatures, and that huge differential creates weather patterns. It can create fog. That's why a lot of times San Francisco gets foggy. Is the temperature of the air and water are either very similar because the water around San Francisco is actually very cold. It's not very warm water at all. This image here shows two Canadian cities, Winnipeg and Vancouver, and the vast differences in their temperatures. Now, Vancouver lies essentially right on the ocean. It's actually in an inlet, but it's very close to the ocean. So their weather, as you can see in this image, is very flat. They don't have the extreme variation that other places would have. You can see it gets, obviously it gets hotter in summer, but for the most part, it's it's not flat, but it's just not as extreme. Now, Winnipeg, which is at almost roughly the same latitude, is far away from the ocean. It's actually just north and west of Wisconsin here. Um, that one they get very, very wild swings. So yeah, it can get very hot in the summer, but it also can get very, very cold here in January. So the idea is that the differential, that moderation comes from being near very large bodies of water, in this case the ocean. So Vancouver doesn't get the wild swings. They sort of have a warmer summer, sure, but they don't have the super cold winters that Winnipeg would have because the ocean moderates that temperature. Temperature also plays a role when depending on what altitude you're sitting at. And I mentioned that earlier when I was working in New Mexico. Here's an example of two cities in South America that have essentially, they're almost at the same latitudes again, but vastly different altitudes. La Paz, Bolivia is one of the highest cities in the world. And you could see here their temperature. So this is over the course of an entire year. It never really gets above 40 degrees in La Paz, Bolivia. Okay. But here's Concepcion, that's further east, but in a more, it's essentially a rainforest. It's like the western edge of the Amazon rainforest. And you could see it barely gets below 70 degrees, here. Oops, sorry, right there. So this is an example of two cities roughly at the same parallel, the same latitudes, but one is vastly higher, so it's always cold. I would not want to live there at all. Here's another example of how um, prevailing winds and being windward or leeward, what that means is, are the winds coming in or are they coming off? In this case, in Eureka and New York City, okay, so Eureka, California is the windward, so the winds are coming in off the ocean, whereas in New York City, the vast majority of the winds are going out to the ocean. Okay, and you can see the big swings again. The ocean plays a huge role in moderating temperatures. So Eureka, California gets pretty much the same temperatures all year long. They have a little bit of variation, but they have essentially the same temperatures all year long because the ocean is moderating it for them. Whereas New York City, they have these wild swings depending on the season because again, their weather patterns are dictated from the west going towards the ocean. The ocean itself is not dictating the weather patterns. This graph shows you the differences in how cloud cover and albedo play a role with each other. So on a clear day, you have high albedo because the sun's able to get directly to the surface, and depending on the surface's sort of the color, like I mentioned earlier with asphalt or a dark roof, it's either going to be absorbed or it's going to be reflected. Now, if you have a clear day, the time of day also plays a role because the highest amount of albedo is going to be here at the hottest part of the day, which is around 3 o'clock in the afternoon. So that's where you're going to get your highest amount of reflected energy. On an overcast day where it's cloudy, you're gonna keep temperatures and everything cooler during the day, and there's much less of a swing. The high is still in the same spot because that's typically the warmest part of the day, but you're not going to get nearly as much reflection back because there's not as much energy being allowed to come down through because it's being absorbed by the clouds. And the other thing with that is clouds, when you have that overcast day, especially in the winter, this plays a huge role in the winter. If you have a cloudy night, you have a tendency to have it not be as cold. Now, if you have a clear night in the winter, that's typically when you get the coldest temperatures because there's all of that energy is just being released back out into space. Human perception of temperature is anything that influences the rate of heat loss from the body or sort of influences the sensation of temperature. It could be air temperature, like right now, if it's summer or winter, the air temperature is going to play a role. Relative humidity, do I feel really dry or am I sweating as soon as I walk outside? The wind, and of course in the winter we have what are called wind chills. So that's the air temperature plus the wind added on top of it to make it feel even colder on your skin. And that's why wind chill is so dangerous. So the colder the temperatures get, and if there's a high wind, you combine those two together, you get frostbite very, very quickly. And then sunshine, the amount of sunshine plays a role because the more direct energy you get from the sun, the hotter you're going to feel. And you go down to Summerfest in the summer on a cloudy day, and yeah, you're okay. You go down there on a super sunny day, and everybody's trying to find shade. That's just how it works with the sun. The sun is hot, and especially in the summer, you get more direct rays, and the sensation is that you're going to sweat and feel hotter than you would with on a cloudy day. Makes sense, right? If you look at the global temperature patterns in the southern hemisphere, the isotherms, or the lines that connect the same sort of temperatures, are much straighter and more stable. And a part of that is because there's a lot more water in the southern hemisphere than there is in the northern hemisphere. So there's a lot of moderation taking place because it might be cold, it might be warm, but the ocean moderates that so that lines have a tendency to be straighter. Whereas in the northern hemisphere, there's a lot more land masses, so things kind of they're all over the place depending on where you are. Now, the annual temperature range is small near the equator. And what that means is it's always hot. It's always hot. They don't get cold, they don't get big swings in temperature. It's almost always the same temperature at the equator, roughly. But as you go away from the equator, either north or south, they start to increase with latitude. So up here where we are in Wisconsin, we can get very warm days. We can get 100 here, and we can get very cold days where it's minus 20 degrees Fahrenheit. And it's greatest over continental locations. Again, because like I've been saying this whole time, over ocean water, the ocean is water and takes much more to heat it or cool it. So those big swings in temperature have a tendency to be over continental locations, especially those that are away from the oceans, like here in Wisconsin. Or in North Dakota, it can get really cold. Those places in the upper Midwest or up into Canada, because they don't have the oceans there to help moderate those temperatures. So here you could see that in the southern hemisphere, like I just mentioned, the isotherms have a tendency to be a bit straighter. There's a lot more ocean. There's a lot less to inhibit it, so to speak, in terms of the ocean keeping everything moderate. But you get a lot more swings when it comes to, let's say, the equatorial regions, although, again, they have a very small variation within those. And you can see here in where we are, it covers a large, going from 70 all the way down to roughly 30 degrees, depending on where you are in January. So because we're over the continental and there's greater variation over the latitudes, so that's why a lot of people go to Florida, for example, in the winter. There's a big difference between Wisconsin and Florida in the middle of January. And finally, this last graphic shows the average sea level temperatures in July. And then in the northern hemisphere, you can see there's a lot less variability here because we're tilted towards the sun. We get a lot more direct sunrise rays. We have warmer temperatures over a much larger period, much larger area, excuse me. And then down in the southern hemisphere where they're having winter, you get much more variability all the way down to minus 40 degrees, way down here, which, ooh, that's cold. But that's in the winter, perpetual darkness in Antarctica. So you got to kind of expect that. All right, so that's it for this chapter. I hope you learned something. The atmosphere, just like everything else on Earth, is both interesting and complicated. There's lots of layers to it, and trying to understand, what the air is composed of in terms of oxygen and nitrogen. Remember, it's mostly nitrogen, even though the human body needs the oxygen to breathe. The ozone layer is very helpful for absorbing the harmful UV rays that come in from the sun. So there's a lot to understand in this chapter in terms of just looking up in the sky and going, wow, what is all this made of in terms of the air we breathe and the sunsets we get and um, the carbon dioxide, the greenhouse gases that we're emitting. We got to keep all those things in mind. So that's it for this chapter, and I'll see you on the next one. Take care.